or it's a function of one or more independent variables. Function of one or more independent variables. So signal itself is a dependent variable. So any quantity is set to be a signal if it is varying with independent variable. You can say that any quantity is said to be a signal if it is a varying with independent variable. For example, AC current, an alternating current, because an alternating current is varying with time. So an alternating current can be considered as a signal. On the other hand, a DC signal is not considered as a signal because it's not changing with time. So signal is a time varying and it varies with time. So we can say that signal is a time varying. Signal is a time varying and it depends on time. So as I mentioned, signal is a dependent or it is a function of some one or more independent variables. So different independent variables and signal depend on time. So time is a varying with independent time. So now there are two different kind of signals. One is continuous time signal, another is a discrete time signal. One is continuous time signal. We can represent as CTS. Another is the discrete time signal. DTS. So one is CTS, one is the DTS. So what is this continuous time signal or CTS? So we can write this continuous time signal. If I go for continuous time signal first, CTS, we can write as x of t. And here t is our independent variable and x is my variable, dependent variable. So if I draw this one like this, so in x-axis we have t, independent time variable, and here we have x. So this is a continuous time signal because the signal is specified. Here, the signal is specified or defined for every value of time, from minus infinity to plus infinity. So, continuous, in case of continuous time signal, signal will be specified for every value of time. This is continuous time signal. Signal will be specified for every value of time. On the other hand, in case of discrete time signal, the signal will be specified at discrete time. For the discrete time signal, DTS, signal will be specified for signal is specified at discrete time, and we can represent it as x of n. So let's say xt is specified as, so for example, this one is specified as t0, t1, t2, tn, t minus 1, t minus 2, t minus 3, to t minus n. So we can draw this one. So this is t0, this is t1, this is t2, this is t3. This is minus t1, minus T2 minus T3. So the signal will be specified at some time interval. So signal is not specified here for every moment of time here. So this is called discrete time signal. So one we have continuous time signal, another we have discrete time signal. So here we can see that there is some time interval, right? There is some time interval, and this time interval can be denoted as del t, right? So we can write down this del t is equals to t1 minus t0. We can write it as t2 minus t1, t3 minus t2, tn minus tn minus 1, like this. So if the time interval is same, if they are all same, if the time interval are same, then we can write down this t1 minus t2 equals to t3 minus t2 equals to tn minus 1, right? We can write this one, fine. So if we look at here, now let's say at t0, the time equals to 0. So then what will happen? T1 minus T0 equals to by time interval, right? So T1 minus 0 equals to T. So T equals to T1. Similarly, we can write down for the next interval 2T. T2 equals to 2T. T3 equals to 3T. Tn equals to NT. We can write this. So here, as I mentioned, this one in the discrete time interval we represent with xn. Here n is the integer value. How we get this integer value? So if you just draw this one, as this is x of nt, now we put the value of n, right? So we have t1 equals to t, this is 2t, this is 3t, this one minus t, this one minus 2t, this one minus 3t. So if you just cancel this t with this t, so it will give you just an integer value, 1, 2, 3. So here, this is very simple one, very basic things. We have a discrete time signal, we have a continuous time signal. Okay. To move forward, we need to understand one more thing that is known as impulse signal. An impulse signal. An impulse signal. What is an impulse signal? An impulse signal is also known as direct delta function. Impulse signal. It is also known as direct delta function. Direct delta function, and it is denoted or represented by delta t. It is represented by delta t. This impulse signal only present at origin. It only present at its origin. It exists or it present at, we can write down, it exists only at t equals to 0. And everywhere else it will be infinite. So we can write down this function, this impulse function, del t is equals to infinite at t equals to 0, or other than it is 0. Okay, so it will be present at only origin. So if I draw this one, we say this is my impulse. Now what is the weight of this impulse, of this strength? usually the area of unit impulse function is always equals to 1. Usually, normally the area of unit impulse function is equals to 1. So this impulse signal is a signal of very short duration. This is important. This impulse function, so its area or distance is 1. This is one of the property of the impulse signal. It is always present at the origin. This is the second property. And the third property is the impulse signal is a signal of a very short duration. It's a very short duration. So now we already see these few things. What is continuous time signal, CTS, what is the discrete time signal, DTS, and the impulse signals. Now, as we are trying to understand the analog to digital conversion or digital to analog conversion, right? That means why we need these things from analog to digital or digital to analog. The all real life signals like the temperature, pressure, speed, even our voice, all are continuous signals. But whenever we want to process it, we need a digital system because it is easy to process the data. So that means a system will work on digital, on a discrete time. That's why we need to convert this continuous time signal into a discrete time signal. Then after processing, again we will convert this discrete time signal to continuous time signal. So this is the whole process. So we need to apply some technique. It's called sampling. So from continuous to discrete time signal, from CTS, continuous time signal, to get to DTS, we need some technique called sampling. By this time, you already understand what is CTS and what is DTS. Okay. So it is a process of reduction from CTS to DTS. This sampling process is also known as a process of reduction from continuous time signal to a DTS, discrete time signal. Because in case of continuous time signal, it will give you every information at every moment. But in discrete time signal, we will get information from individual time period. So, but important point is that we need to recover this signal again. This is important. We can sample it, but important point is that after processing, we need to recover our original continuous time signal. So, for doing that, we should have some conditions. So let's try with how we can convert this complex CTS to DTS by sampling. So for example, this is my continuous time signal. For example, our message signal, our voice signal, empty. Yes.
We're converting from CTS to DTS, then again converting to CTS?
Yeah, we need, because, for example, you are hearing music. So somebody is singing. This is a continuous signal. Then they process it, they amplify it, they transfer it. But when again you are hearing, you are getting the voice. You are not hearing the song, you are hearing a whole signal, right? So it is continuous signal. So we need to process it, CTS to DTS, then we need again send it back to CTS. That's why we need to recover.
During this recovery, does it loses the...
Yeah, there is a noise, of course. So we need to amplify the signal just before sending it, and just after receiving it, we need to again amplify. And another thing, we need to check whether our signal is intact or not. This is called, whenever we talk about in our communication class about this amplitude modulation, there are different kind of techniques to send this data. And if you want for analog modulation, there is amplitude modulation, there is a frequency modulation, there is a phase modulation. If you want to send it by digitally, there is called PPM, PTM, PCM. So it's up to you. So usually, whenever you use the optical fiber lines with the digital communication system, so then we use the PCM, pulse code modulation technique, or PPM, pulse phase modulation technique like this. If you want to send it through this air-free space, we usually use, because for example, you are trying to send your communication channel, establish your communication channel through the satellite. So you are not sending by optical fiber, right? So using this free air space. Then we use the frequency modulation technique or the amplitude modulation technique. But in the amplitude modulation technique, they are very much sensitive to noise. The noise easily can get integrated into our signals. So this is totally different. Of course, we have those problems that we have to design our circuit like that it will have minimum noise. Then we have to calculate the signal to noise ratio is supposed to be less than 1. We calculate those things. Bit error rate. In case of digital communication, we have a bit error rate like that. So anyway, so this is our continuous time signal for our message signal, our voice, MT. Okay, so this is time, and this is continuous time signal. Okay, so this signal is carrying our information. Okay. So for processing this signal, we must have a band limited signal. That means our circuit cannot process a continuous signal from -infinity to +infinity. To process this continuous time signal, we should have a finite range of signal. And to get a finite range of signal is known as band limited signal. This is band unlimited signal, because here we are going from -infinity to +infinity. So it's unlimited, band unlimited. But from here we have to have a band limited signal. How we can get that? We can get that by using a low pass filter. A low pass filter. It is also known as anti-aliasing filter. If you pass it through a low pass filter or a Fourier transformation, this is in time domain, then you will get a signal, a band limited signal. This is known as a band limited signal. Then it is in frequency domain. Here we have omega n, here we have minus omega n. So what is a band limited signal? Band limited signal is the Fourier transform of a message signal, and here the spectrum of the message signal is non-zero only within a small range of frequency. In the band limited signal, the spectrum of the message signal is non-zero only for a limited frequency. That's why it is known as band limited signal. Before sampling, we have to have these things. So before sampling circuit, we need to send our signal through a low pass filter. So it will convert your band unlimited signal into a band limited signal. A band limited signal is a signal of the spectrum of the message signal where, a band limited signal is a signal where the spectrum of the message signal is non-zero only within a small range of frequency. Okay. So here, this is Fourier transformation. Here we can see this is a time domain. Now it's transferred to a frequency domain. And here omega n is our maximum message frequency. Omega m is our maximum message frequency. If you send a multi-tone signals, that means if your channel have more than one signals, then it will consider the maximum of that all the channels, among all the channels. So if you have 3 signals, F1, F2, F3, if F3 is higher than F2, F2 is higher than F1, your omega n will be F2. Your omega n will be F2. So this is the maximum message signal frequency. So here frequency 0, so here frequency, you're getting the frequency, right? Okay. And these are the side bands. If you have the communication class, these are the side bands. Omega n plus omega n minus omega n. So the 2 side bands. Okay. So here we can say we are having a finite range of spectrum or finite range of frequency. Here we have a finite range of frequency. So this is the first step of the sampling. We need to pass our, yes sir.
No.
We have to pass our continuous time signal through a low pass filter to get a band limited signal.
Okay, I have it.
Yeah.
So you are saying WM is the maximum message frequency. Then
So you have
it's
is
it positive? It's for both side, or it's the positive
it's
and
a mirror image.
Okay.
It's a side band, upper side band and a lower side band. So whenever we do this Fourier transformation, so it is a long equation. It's like if you apply the trigonometry, you will get a cos of omega m plus omega s. Then in this side, you will get omega m minus omega s. So one will be upper band, one will be the lower band. Okay. So this is a band limited signal, and here omega n is the maximum frequency component of the message signal. So to get this band signal, we have to use
So if F3 is the maximum WM, negative WM, does the value of F2 and F1 have to be non-zero, or can it still be zero?
Which one? So this one, in between this one, they are non-zero.
Those are non-zero, but does everything between them also have to be non-zero?
No.
Okay.
So here the bandwidth is twice of WM. The bandwidth is total. This is the one of the drawback of a double sideband surface carrier. This is called, as I mentioned you, whenever we send a signal using the communication channel, we have to use the amplitude modulation, right? In the amplitude modulation, we need to send this signal. So in the amplitude modulation, the bandwidth is twice of the message signal. Twice of the message signal. This is the total bandwidth. Twice of the message signal. Not this one, also this one. So what we need a low pass filter, and this low pass filter is also known as anti-aliasing filter. This low pass filter, in short we'll write it LPF. This LPF is also known as anti-aliasing filter. If we don't have this anti-aliasing filter, maybe some frequency from other band will get interfered. So here we're trying to send this frequency. If we don't use the low pass filter, maybe some of the frequency from this side or some of the frequency from this side will get interfered with our original message signal. So that's why we need to pass the band unlimited signal to a low pass filter to get a band limited signal. Of course, we already know what is our range, what is our requirement, what is the channel we want, right? Okay. 20. Usually our voice is from 20 Hz to 20,000 Hz, right? 20K.
20K.
Yeah. So this is the range. So we'll use this filter before sampling. Then we'll use the sampler. So what is the sampler? So once you have this low pass filter, then we'll give it to the sampler circuit. A sampler is a circuit. It is just a multiplier. It is just a multiplier. So that means it will multiply two signals, and both of these two signals will be continuous time signal. So this is the thing. Whenever we have this signal in time domain, my message signal, right? After Fourier transformation or by passing through a low pass filter, we are getting a band limited signal, right? This one, but this one is still a continuous time signal, okay? This is not a discrete time signal. This is just a band limited signal. Okay, don't get confused with this one. So in the multiplier, in the sampler, so this is the box diagram of the sampler. And as I mentioned, it's just a multiplier, so it will multiply two signals, two continuous time signals. One is our message signal, empty. So just for, we can see this one. Of course, we just pass it to a low pass filter, then it is split into the sampler circuit. What about the other one? The other one of this sampler is known as the periodic impulse train. That's why we talk about that impulse. So other signal will be our periodic impulse train.
The triangle, I forgot, the filter,
Band limited signal.
band limiter signal. So we're using the band limited signal to capture our infinite bandwidth.
To a finite range.
Then we're okay. Got
So
it. Got
if I
it.
draw here, okay, no problem. So this is low pass filter. Okay. Here we are giving this band unlimited signal. Okay. Then we are getting a band limited signal. Then we predict this band limited signal here.
What happens if it's not? If the frequency is not in the band, what will happen?
No, that's why we have to design your low pass filter, right? Whenever you will design your low pass filter, there will be cutoff frequency. So you will already know what is your cutoff frequency, which band you want to get this infinite range. Okay. So it's a low pass filter. It's an LC circuit. So you just know how to design the circuit. Depending on your required frequency, you will choose the L value and C value.
Okay.
Okay. Or even you can. I think you can design with the RC circuit as well.
Then you pass it to the
The sampler, a device or tool called sampler.
sampler.
Sampler is nothing but a multiplier.
Multiplier.
It will multiply your two continuous signal.
Okay.
Two continuous signal. It will multiply your two continuous signal.
Got it.
Okay. So one is my message signal, a band limited signal. One is my periodic impulse pulse. So what is this periodic impulse pulse? This periodic impulse pulse we can denote it with delta. We can write down as an equation Ct is equals to delta t minus nts, where n equals to minus infinity to plus infinity. So we already talked about the impulse, right? Impulse signal. Impulse signal will be appear only at origin. It has unit strength, right? So if we put this value here, I'll show you. But here, this Ct has fundamental time period. This Ct has fundamental time period Ts. This one. So from here we can say that this angular frequency of this sampling, angular frequency of this sampler omega s is equals to twice pi by Ts.
TS.
Right? So Ts is my fundamental time period. So we have two frequency. One is the maximum message signal frequency. You have to be very careful that this is the maximum, not only the message frequency. This is the maximum message frequency. And another is the sampling frequency. So now we can see here how we get this impulse. For example, when t equals to 0, sorry, when n equals to 0, when n equals to 0, we can say Ct equals to delta t. When n equals to 1, so if when n equals to 0, we are getting Ct equals to delta t. That means impulse present at Ts, right? So impulse at this moment, impulse present at origin. Now when n equals to 1, what will happen of Ct? It will be del t minus Ts. That means impulse will present at Ts time. So if it is like that, we can draw these impulses like this. So at 0, it is del t. Then we will have this one as Ts, it one as 2Ts, 3Ts, it will be minus Ts, minus 2Ts, minus 3Ts. So this is the impulse stream we are giving. So impulse stream, because this is not only one signal, this is known as impulse stream at fundamental time period of Ts. So we have two continuous time signal. One is my maximum message frequency, and another is the sampling frequency. Okay. What about the impulse weight? The weight will be equal to the instantaneous value of our message signal, because we are trying to sample it, right? So the weight will be instantaneous value of our message signal. So this is the new signal. So it will give you the output, and the output is denoted by sampling signal. So it will be as t, right? So as t equals to mt times what? Ct, right? This is my Ct. This is my MT, this is ST. Because it's just a multiplier, so it will give you the product only. So now we'll find out the spectrum of the ST. Now we need to find out how the spectrum would look like. We know the spectrum of this one. This is the spectrum, right? So if it is in time domain, we should not draw this one. If it is in, as this is still in time domain, we should draw like this. We give this one, we give this one in the time domain. Now we have to have this spectrum for ST, right? Okay. So that means we need to find out the Fourier transformation, because you have to, if you want to get the spectrum in the frequency domain, what we need to do? We need to transform it from time domain to frequency domain, and we can do that by using a Fourier transformation. So that means we need to do the Fourier transformation that will give you ST to S omega. Here we already have this time domain to frequency domain. If I just draw it here, this is my message signal, MT. Then we already have our, M omega m to minus omega m. So we already have this one. Now we need this one. So we can write down this equation as 1 by twice pi m omega to C omega. Whenever we have in time domain, that was just a product form, right? MT dot Ct. But whenever we go for the Fourier transformation, it is known as convolution. This star sign is known as a convolution. So here we already have our m omega. M omega is our hand. So we need to have this C omega. That means from the continuous time signal to the Fourier transformation, we need to convert it to the Fourier transformation. Okay. So how we can get this C omega now? So we can write down this C omega is equals to omega S. If I write down the Ct equation again first here, it will be good. Our Ct was minus infinity to infinity delta T minus Ts. So if you want to This is in time domain. We need to make it in a frequency domain. C omega equals to omega s and minus infinity plus infinity delta omega minus n omega s. Right? So our s omega was 1 by 2 pi m omega times c omega, right? Oh, sorry, convolution c omega, which is omega s n minus infinity delta omega minus n omega s. This one. So as this is also constant, then we can take it here s omega here omega s by 2 pi m omega convolution of n delta omega minus n omega s. So omega s by 2 pi is 1 over ts. So s omega equals to 1 over ts. Then if I write down this, take this one summation sign here, n minus omega to omega and omega convolution of delta omega minus n omega s. Then in a Fourier transformation there are several properties. One of the properties is like that. One of the properties of the Fourier transformation saying that if we have xt convolution of delta t minus t1, it can be written as x of t minus t1. If we have a signal xt and the signal is convoluted by delta t minus t1, then it is equal to x of t minus t1. So same thing is here. If you consider this is x convolution of delta x minus xt. So we can write this equation as I'm coming from here to here. S omega equals to 1 over Ts summation of n to the power minus infinity to plus infinity m omega minus n omega s. So we got our equation here. So what is this one? This is my output of the sampler circuit, right? If you can remember, we have the sampler circuit here. In the sampler circuit, we give our MT in time domain. We give our CT in time domain. Of course, we give it through after frequency domain for your transformation. Then we already see if I give this signal as well in the frequency domain, what will happen? Then it will give you sampling in time domain. Now we are trying to get the sampling frequency S omega. So if this is S omega. So in S omega, if you put the value of n, when n equals to 0, what we can see, when n equals to 0, this whole term will be 0, we'll get m omega. What is my m omega? M omega is nothing but our message signal. If you can remember. That was my signal, right? Message signal in frequency domain. So you are getting like this m omega. But with that, we will also have some other band, upper band and lower band. So if you put n equals to 1, if you put n equals to 1, we'll get, when n equals to 1, s omega will be omega minus omega s. So it will shift to the left. So that means it will have here m omega minus omega s. If you go minus 2, minus 3, you will get. And if you put n equals to minus 1, so minus 1 plus m plus omega s.
Yes.
We will get s omega plus omega s. So we can keep continue with other terms like this. Like other term. From minus infinity to plus infinity. So this is my output of the sampling circuit or the sampling frequency in the frequency spectrum. So from this equation, we can draw this spectrum. Now we have this equation. Now we can easily draw the spectrum. So if I draw the spectrum here, okay, I just write down the equation upside. I draw the. So we already have our s omega is equals to 1 over Ts plus m of omega minus omega s plus m omega plus m of omega plus omega s like this. Now I want to get this spectrum. So let's say this is my spectrum. So when n equals to 0 at the origin, we are getting m omega. So we are getting, this is my s omega, right? Sampling frequency. In the sampling frequency, we have this frequency component, m omega at origin. Now my sampling frequency shift to right and left. Shift to left, right, so right and left. How much? By omega s. So if it is, this one is omega s, and that is another minus omega s. So now we'll get an omega s plus omega n, omega s minus omega n. This is the range of minus omega s plus omega n, and this is the minus omega s minus omega n. Of course, it will continue to minus infinity to plus, right? So we already get our spectrum from this equation. We're just thinking about only 3 components, okay? So that will have m minus 2 omega s. Here we'll get m plus 2 omega s. It will continue. This is the important thing. So from the graph, what we can see? From the graph, we can see this. So this is starting from 0, origin. This is one frequency point. For example, maybe 1 kilohertz or 1 megahertz, whatever it is. Then it is 1.5 megahertz, something like that, right? So we can write this from this curve, from this graph, we can write down this omega s minus omega m. This point, omega s minus omega m is greater than omega m, right? This point is greater than this point. This one is high frequency component. This is low frequency component. So from here we can write down this omega s is greater than twice of omega s. What is omega s?
Sampling frequency.
My sampling frequency. What is omega m? My
Cutoff
maximum
frequency.
message frequency. So my sampling frequency should be greater than twice of my maximum message frequency. If it is like that, then there is no overlapping and there is also a gap. And this gap is known as guard band. This gap is known as guard band. this is the best situation. They are not overlapping. My message signal is intact, no problem. Another thing can happen, something like that. Is just touch. This is omega s, this is omega s plus omega m, and this point is also omega s minus omega m, right? So I'm not drawing this part, this will be same, okay? I'm not drawing this part. I'm just showing you the right upper band side. So at this situation, we can see that omega s minus omega n is equals to omega m. There is the same frequency component. So we can write down this omega s equals to twice of omega n. Previously we saw that omega s greater than twice of omega n, right? Now we saw that it is omega s equals to twice of omega n. Still they are not overlapping, but this is the range. So sampling frequency should be greater than or equals to twice of omega n. And from here we can draw our sampling theorem and definition. A signal can be represented in its sample and can be recovered back when sampling frequency is greater or equal to twice of maximum frequency component present in signal. So this is the definition of this signal sampling theorem. That means you can make a discrete time signal. We are trying to convert it, right, from CTS to DTS. But there should be some conditions so that we can recover it. So condition is like that. And from this equation, from this condition, we can make a definition. A signal can be represented in its samples and can be recovered back when sampling frequency is greater or equal to twice of maximum frequency component present in signal. But if it is not happen, what will happen? So you can see here, if I draw this one, right? So in this case, what you can see, omega
S minus omega is less than omega.
So we lost this portion of our signal. Similarly, it will also come here, right? Sorry. It will also fit here. So we can draw this one as well like this. It's a mirror image. So if this happens, we lost our message signal. We cannot recover our message signal as it is. Okay. So we can write 3 steps here. From this theorem, we can see 3 things here. One is known as oversampling. Oversampling when sampling frequency is greater than twice of omega n. We can represent in frequency form also. This is angular frequency. We can also write it Fs is greater than twice of Fm. This is oversampling. Another is known as undersampling. In undersampling, omega s should be less than twice of omega n, or Fs is less than twice of Fm. And the third one is known as, when they are equal, is known as Nyquist rate. A Nyquist rate. When omega s is equals to twice of omega n. So the definition of this Nyquist rate is the minimum sampling rate. So this is the minimum. Otherwise, we cannot recover our message signal. So the minimum sampling rate, omega s equals to twice of omega m, or fs equals to twice of fm, required to recover message signal is known as Nyquist rate. The minimum sampling rate required to recover the message signal is known as Nyquist rate. So Nyquist rate, whenever you see the Nyquist rate, this is the minimum. There is no guard band, but still they are not overlapping. We can get back our message signal. Okay? But if it is less than that, we'll actually lose our signal. So these are the three things we have. So I will take a break, then we'll see how we can recover our message signal. Here we already sampled it, right? Now we need to recover it. I'm coming back. Conditions to get a signal, a continuous time signal into a discrete time signal, sample it in such a way that we can recover it back. We can recover it back, right? So to recover it back, either we have to have this minimum sampling rate, which is known as Nyquist rate, which is omega s equals to twice of omega m, or fs equals to twice of fm. Or it's better if we have this over something, omega s equals to twice of omega m. So that will be a guard band. So here we can see that we have that why we talk about this continuous time signal and the discrete time signal. In the continuous, this was on my signal. Then we give it to the sampler. We give the impulse signal as well. Once we get this impulse signal, the strength of the impulse signal is equals to the instantaneous value of our message signal, right? So our impulse was like that. But when you have the multiplier, it's supposed to have some value, something like this. So we get something like this. So this is called continuous to discrete time signal, CTS to DTS. Now we will try to obtain the message signal empty from the Fourier transform of the sample signal. We have the Fourier sample S omega, so we already have S omega now. We need to get back our message signal empty. So to do that, we again need to fit this S omega or sampling frequency into another low pass filter. We need to fit this into again a low pass filter. That means this is my sampler. In the sampler, we give CT, we give MD, and it gives us ST, then we have S omega. Then we fit this S omega or sampling frequency into a low pass filter. So we just think this is an ideal low pass filter. So the ideal low pass filter has some characteristics. So the frequency response of this ideal low pass filter, we can think this is the characteristics of the ideal low pass filter. Omega C to minus omega C. Omega C is here, is the cutoff frequency. Omega C is my cutoff frequency. And this is an ideal, it should be very sharp. Usually it will not sharp, but we just think this is a sharp ideal low pass filter. So as here we are giving S omega, what is H omega? And here we get our message. So I just put R, that means recovered message, MR omega. Right? Okay, right. This is again a low pass filter acting like again multiplier sense. Okay, it will just give you. So we can write down this H omega is nothing but m r omega by s omega, or we can write down this m r omega equals to h omega times s omega, right? M1 is recovered message. So it is still in the frequency domain. Okay, still in the frequency domain. It is easy to understand or analyze in the frequency domain. That's why we are in the frequency domain. So if you look at here, the characteristics of this filter, low pass filter. So here, like this, right? From minus infinity to minus omega c, it is 0. Minus infinity to minus omega c, it is 0. Again, from omega c to plus infinity, still it is 0. Omega c to plus infinity, it is 0. Right? And we have already our s omega, right? So if I draw both these spectrum, s omega. So we just consider overlapping, okay? Plus infinite omega s plus omega m, omega s minus omega m, here omega m 0 minus omega m, here minus omega s plus omega m, and this is minus omega s minus omega m, this is minus omega s. That was my sampling frequency. Here we also have our low pass filter. This is minus omega c, this is omega c. So this is my plus infinite to minus infinite. Right? We have this together, and my message, recovered message, is nothing but s omega times h omega. So here, if you look at here, so if I just extend this line, so from minus omega c to omega m is 0. That means from infinite to until omega m, everything is 0. This is multiply. If you multiply this one with this one, until here we get 0. So we can get from minus infinity to until omega minus omega m, we'll get 0. Similarly here, whenever you multiply these things, from minus infinity to this one, as this one is 0, so here this portion is 0. If you multiply these two, you will get 0. So that means minus plus infinity to omega n, you still will get 0. So plus omega n to plus infinity is 0. So the product will give you only this portion. So you get back your message signal. Now if you just do the inverse Fourier transformation, it will give you in time domain. So this is how we can get recovery. So here we can write down few things. So these are few conditions we can look at. So the condition to recover back is this omega c, right? We got it omega c here, right? If I just extended line, it was omega c, this was minus omega c, right? So the condition is omega c should be less than omega s minus omega m, but should be greater than omega m. So your cutoff frequency of your filter should maintain these things. This is your cutoff frequency of your low pass filter. This is supposed to be higher than omega m, maximum message frequency, but lower than this omega s minus omega n. So if you don't have, for example, what will happen, so we have so many conditions. One is omega c equals to omega n. One can be omega c equals to omega s minus omega n. And then omega c greater less than omega n. And the one is omega c greater than omega minus omega n. So if I try to draw this one, the first condition is omega c equals to omega n, right? So omega c equals to omega n means my filter, sorry, cutoff frequency is like this. Still we can recover our message signal. So this is okay, this condition. Then you can design your filter according omega c cutoff frequency equals to omega s minus omega n. Omega s minus omega n. So this is omega s minus plus omega n. So here it will be like this. We can just extend this one. Still we can recover. So this is also okay. But when omega c is less than omega n, that means your filter now, you design your filter here. So we will not recover your signal. We lose your signal here. Or if you design your, so this is not correct. Or if you design this, sorry, this is omega c is greater than omega s minus omega n. So the last one. So it will interfere from the upper band or the lower band. So there will be some interference, noise. So these two conditions must be fulfilled. So this is how we can design our sampling circuit or sampler circuit. So we will have at first a low pass filter for the anti-aliasing, or it is also known as anti-aliasing filter. So we can get a band limited signal. Then we will give it to a sampler circuit. In the sampler circuit, we will see in our next class we need to do more things after sampling, because we are trying to get analog to digital or digital to analog. Then we need to give some values. This is known as quantization. After quantization, we need to give some coding, the bits, digital values. It's called encoding. So we need to do those processes. That's why we have to have a circuit called sample and hold. Sample and hold. After sampling, we need to do those processing. So that's why at that moment, we need to hold that information before getting the next sample. After holding that, we'll give it to this data. But if you want to get recovered back on the other side, we need to we'll see that. But one option is that we have to have another low pass filter, so that we can get back our sample signal. So that's all. So next class we'll talk about test quantization and the encoding. And hopefully I will finish the sampling. Then we'll move to the circuit that we will use for converter.
Can you provide us some images how the flow of diagram, how they are represented of the sampling? Some diagrams.
Yeah, I will hand over this one, hand notes, and I will upload one PPT file. Thank you.
Is this formula is in the book?
Yeah, it's in the book.
And then it's fine. So we can understand by reading the book.
Yeah.
Then okay.